Hello there and welcome to Sleep Science Chronicles. Tonight we're going on a journey to one of the strangest boundaries in the universe, a place where the rules of space and time bend so completely that they almost trade places, where gravity becomes so strong that not even light can climb back out, where time itself, from the perspective of someone watching from far away, stretches toward infinity. We're exploring event horizons, the invisible edges of black holes. You might think of a black hole as a thing, a cosmic vacuum cleaner pulling everything toward it, but that's not quite right. A black hole is better understood as a region of space-time so warped, so deeply curved, that it creates a boundary. And that boundary, the event horizon, is not a wall or a surface. It's something stranger. It's a point of no return written into the geometry of the universe itself. This evening, you don't need to understand the mathematics, though we'll touch on some of it gently. You don't need to visualize the impossible, though we'll try. All you need to do is rest. Let your mind wander through these ideas the way light wanders through curved space. Some facts will feel familiar. Others will feel beautifully strange, and that's exactly as it should be. An event horizon is a place where our everyday intuitions about cause and effect, about past and future, about here and there, all begin to break down. It's a place where the universe reveals something fundamental about the nature of reality. And tonight, we'll explore what that boundary means, what it is, how it forms, what happens there, and why, in some profound sense, an event horizon is the most patient place in the cosmos, where time, for those watching from outside, never quite runs out. Before we begin, if these calm, curious explorations of the universe help you unwind or give you a quiet way to rest your thoughts, consider liking and subscribing to the channel. It helps others find their way here too, one sleepy soul at a time. But for now, let your breathing slow. Let the day fall away. And let's step toward the edge of the knowable. An event horizon is not a physical surface. You could not touch it, stand on it, or bounce a ball against it. It's a boundary in space-time itself. Think of it as an invisible line that marks the point where escape becomes impossible. On one side of that line, you could still fire your rockets, turn around, and leave. On the other side, every path you could possibly take leads inward. The event horizon is the dividing line between those two regions. This boundary exists because of gravity. Gravity, as Einstein showed us, is not a force pulling objects together. It's the curvature of spacetime caused by mass. A planet curves spacetime a little. A star curves it more. And a black hole curves it so extremely that spacetime folds in on itself, creating a region from which nothing can escape. The term event horizon comes from the idea that events occurring beyond that boundary cannot be seen by observers outside. Any light emitted beyond the horizon stays beyond it. Any signal sent outward gets pulled back inward. The horizon is the edge of what can be observed. Beyond it, events happen in a place forever cut off from the rest of the universe. The simplest kind of black hole, one that doesn't rotate and has no electric charge, is called a Schwarzschild black hole. It's named after Karl Schwarzschild, a German physicist who found the first exact solution to Einstein's equations of general relativity. Remarkably, he derived this solution in 1916, just months after Einstein published his theory. And even more remarkably, he did it while serving in the German army during World War I. Schwarzschild's solution describes the space-time around a perfectly spherical, non-rotating mass. For most objects like Earth or the Sun, this solution applies outside the object's surface. But if you compress enough mass into a small enough space, something strange happens. The solution predicts the formation of an event horizon, a point where the curvature becomes so extreme that the geometry itself changes fundamentally. The size of the event horizon depends only on the mass of the black hole. This distance from the center is called the Schwarzschild radius. The formula is simple and elegant. The Schwarzschild radius equals 2 times the gravitational constant times the mass divided by the speed of light squared. For a black hole with the mass of our Sun, the Schwarzschild radius would be about 3 kilometers. If you could somehow compress the Sun down to a sphere 6 kilometers across, it would form an event horizon. The Earth, if compressed to form a black hole, would have a Schwarzschild radius of about 9 millimeters, less than a centimeter. A marble-sized event horizon containing the entire mass of our planet. Of course, this is purely theoretical. There's no known way to compress Earth or the Sun to such densities. But the mathematics tells us that if you could, an event horizon would form. The event horizon of a non-rotating black hole is perfectly spherical. It exists at the Schwarzschild radius in all directions from the center. This sphere marks the boundary. Inside, all paths lead to the singularity at the center. Outside, escape is still possible if you're moving fast enough. Exactly at the horizon, you would need to move at the speed of light to escape. And since nothing with mass can move at the speed of light, nothing with mass can hover at the event horizon. Light itself behaves strangely near an event horizon. Photons, particles of light, always travel at the speed of light. But the paths they follow, called geodesics, are determined by the curvature of spacetime. Near a black hole, spacetime is so curved that light paths bend dramatically. Light emitted outward from just above the event horizon barely escapes. It climbs out of the gravitational well, losing energy and becoming redder and dimmer as it does. Light emitted exactly at the event horizon has a strange fate. It neither falls in nor escapes. It orbits the black hole right at the boundary, traveling in circles at the speed of light. This is a mathematical quirk of the geometry. In practice, the tiniest perturbation would send that light either inward or outward. But in the perfect idealized case, light at the horizon moves in place, so to speak. Light emitted from inside the event horizon cannot escape, no matter which direction it's aimed. Even a photon aimed directly outward, moving at the speed of light, gets pulled back inward. This sounds paradoxical. How can light, moving at the maximum possible speed, fail to escape? The answer lies in the geometry. Inside the event horizon, the future direction of spacetime points inward. Moving forward in time means moving toward the singularity. There is no outward path through spacetime once you're inside. This is what makes an event horizon a true point of no return. It's not that gravity pulls so hard that even light can't escape. It's that the structure of spacetime itself has changed. The direction we call inward outside the horizon becomes the direction we call future inside the horizon. Falling toward the singularity is as inevitable as moving forward in time. The speed of light is the universe's speed limit. Nothing can move through space faster than light. This fact, combined with the curvature of spacetime at the event horizon, creates the boundary. At the horizon, you would need to move at the speed of light just to stay in place. Inside the horizon, even moving at the speed of light isn't enough to escape. The geometry is warped so severely that all possible futures lead inward. Einstein himself was skeptical that black holes could exist in nature. He believed the mathematics, but he thought that some physical process would prevent the formation of such extreme objects. He published a paper in 1939 arguing that stars could not collapse to form singularities. He was wrong. We now know that massive stars at the end of their lives can indeed collapse to form black holes, and we've detected them throughout the universe. The term black hole wasn't coined until 1967 by physicist John Archibald Wheeler. Before that, they were called frozen stars or collapsed stars, or simply Schwarzschild singularities. Wheeler's term captured the public imagination: a hole in space, a region of darkness. But it's worth remembering that it's not a hole in the usual sense. It's a region of extreme curvature, and the blackness comes from the fact that light cannot escape the event horizon to reach our eyes. Event horizons are invisible. They emit no light and reflect no light. The only way to see an event horizon is by observing its effects on nearby matter and light. Gas falling toward a black hole heats up and glows brightly, forming what's called an accretion disk. This disk surrounds the event horizon, and the event horizon itself appears as a dark circle silhouetted against the glowing gas. This silhouette is what the Event Horizon Telescope imaged in 2019 when it captured the first picture of a black hole's shadow. The Event Horizon Telescope isn't a single telescope. It's a network of radio telescopes around the world, working together to create an Earth-sized virtual telescope. By combining observations from multiple locations, astronomers achieved the resolution needed to see the shadow of the supermassive black hole at the center of the galaxy M87. That shadow is about 2.5 times the size of the event horizon itself, due to the bending of light around the black hole. What the Event Horizon Telescope showed us was not the event horizon directly, but the absence of light where the event horizon should be. The dark circle in the image is the shadow cast by the event horizon. Light from the glowing gas behind and around the black hole gets bent around the event horizon, creating a bright ring. Inside that ring, there's darkness. That darkness marks the region from which no light can escape. The size of the shadow depends on the mass of the black hole. The black hole in M87 has a mass about 6.5 billion times the mass of our Sun. Its event horizon has a diameter of about 38 billion kilometers. That's roughly the size of our entire solar system. And yet, even something that large appears as only a tiny shadow in the sky, because M87 is about 55 million light years away. At the center of our own galaxy, the Milky Way, there's a supermassive black hole called Sagittarius A star, or SGRA star for short. It has a mass about 4 million times the mass of the Sun. Its event horizon is much smaller than M87's, with a diameter of about 24 million kilometers. The Event Horizon Telescope imaged SGRA star as well, though the image was more challenging to produce because the gas around SGRA star changes rapidly, sometimes in just minutes. Every large galaxy seems to have a supermassive black hole at its center. These black holes have masses ranging from millions to billions of solar masses. How they grew so large is still a topic of research. They might have formed from the collapse of massive clouds of gas in the early universe, Or they might have started as smaller black holes that grew by accreting matter and merging with other black holes over billions of years. Stellar mass black holes, formed from the collapse of massive stars, are much smaller. A black hole with 10 times the mass of the Sun would have an event horizon with a diameter of about 60 kilometers. That's tiny compared to supermassive black holes, but still strange to imagine. A city-sized sphere containing 10 times the mass of the Sun, with an event horizon marking the point of no return. The event horizon is often described as the point where the escape velocity equals the speed of light. Escape velocity is the speed you'd need to leave a gravitational field without using any additional thrust. On Earth, the escape velocity is about 11 kilometers per second. For the Sun, it's about 618 kilometers per second. At the event horizon of a black hole, the escape velocity reaches 299,792 kilometers per second, the speed of light itself. And since nothing can exceed that speed, nothing can escape. But this description, while useful, is a bit misleading. It makes it sound like escaping from a black hole is just a matter of going fast enough. In reality, the problem is more fundamental. Inside the event horizon, there is no outward direction in space-time. It's not that you're not going fast enough. It's that every possible path you could take, no matter how fast you move or which direction you aim, leads inward. This is one of the most profound insights of general relativity. Gravity isn't a force pulling you inward. It's the curvature of space-time telling you which directions you can move. Near a black hole, space-time is curved so extremely that the inward direction becomes unavoidable. At the event horizon, the curvature is so severe that the future direction of time points inward. Moving forward in time means falling toward the singularity. Imagine you're in a river, floating downstream. Far from a waterfall, you could swim to shore. Closer to the waterfall, the current gets stronger, but you might still escape if you swim hard enough. But at a certain point, the current becomes so strong that even if you swim at your maximum speed, you'll still get pulled toward the waterfall. That point, where the water's speed equals your maximum swimming speed, is analogous to the event horizon. Beyond that point, every possible action you take still results in going over the falls. Now imagine that instead of a river, the waterfall is carved into the structure of time itself. Beyond a certain point, every future moment pulls you closer to the edge. There is no swimming against time. There is no staying in place or moving backward. The event horizon is the point where the future becomes a one-way path toward the center. This is why the event horizon is sometimes called the surface of no return. But calling it a surface is misleading. It's not a membrane or a barrier. If you were falling toward a black hole, you wouldn't feel anything special as you crossed the event horizon. Locally, space-time would seem smooth and continuous. You wouldn't notice any jolt or change. From your perspective, you'd simply continue falling. It's only from the perspective of someone far away that the event horizon represents a boundary. For an outside observer, someone watching from a safe distance, something very strange happens as an object approaches the event horizon. Time dilation, a consequence of general relativity, becomes extreme. As an object falls closer to the event horizon, time for that object appears to slow down from the outside observer's perspective. The object appears to move more and more slowly. Its light becomes more and more redshifted, shifting toward longer wavelengths, and dimming. At the event horizon itself, from the outside observer's perspective, time dilation becomes infinite. The falling object appears to freeze, hovering just above the horizon forever. Its light becomes infinitely redshifted, fading to invisibility. No outside observer will ever see the object actually cross the horizon. They'll see it slow down asymptotically, approaching the horizon, but never quite reaching it. The event will take infinite time from the outside perspective. This effect is real, not an illusion. It's a consequence of how time flows differently in different gravitational fields. Strong gravity slows time. Near the event horizon, gravity is so strong that time, as measured by a distant observer, slows to a stop. The mathematical limit is clear. As you approach the Schwarzschild radius, time dilation approaches infinity. At exactly the radius, time stops from the outside view. But from the perspective of the falling object, time continues normally. If you were falling toward a black hole, your watch would tick at its usual rate. Your heartbeat would continue as always. You wouldn't experience time slowing down. You'd cross the event horizon in a finite amount of your own time, called proper time. For a stellar mass black hole, this might take only a fraction of a second. For a supermassive black hole, it might take hours. This creates a paradox of perspectives. To you falling in, you cross the horizon in finite time and continue falling toward the singularity. To someone watching from outside, you never cross the horizon. You freeze at the edge, fading from view over infinite time. Both perspectives are correct within their own reference frames. This is one of the strange consequences of relativity. There is no universal now. Time is relative. Different observers can disagree on the order and timing of events. Imagine you're falling toward a black hole and sending radio signals back to a friend orbiting safely far away. You send signals once per second by your watch. As you get closer to the event horizon, your friend receives your signals less and less frequently. Time dilation causes the signals to be spaced further apart from their perspective. Near the horizon, the signals become minutes apart, then hours, then days. The last signal you send just before crossing the horizon from your perspective takes infinite time to reach your friend. From their perspective, they never receive it. Or more precisely, they would need to wait forever to receive it. Every signal you send after crossing the horizon never escapes at all. Those signals fall inward with you. Your friend's last view of you is a frozen image, fading and reddening, hovering just above the horizon forever. This effect was once called asymptotic freeze. Before the term black hole became popular, some scientists called these objects frozen stars because, from an outside perspective, a collapsing star appears to freeze just as it reaches the Schwarzschild radius. The collapse appears to halt, suspended in time. But this is only from the outside view. From the perspective of matter in the collapsing star, the collapse continues, the event horizon forms, and everything falls toward the singularity. Time dilation near massive objects isn't unique to black holes. It happens around any mass, but the effects are usually tiny. On Earth's surface, time runs slightly slower than it does in orbit. GPS satellites have to account for this effect. Their clocks run faster than clocks on the ground because they're in a weaker gravitational field. The difference is only microseconds per day, but it's measurable and important for accurate navigation. Near a neutron star, time dilation is more significant. A neutron star is incredibly dense, but not quite dense enough to form an event horizon. Gravity at the surface of a neutron star is about 100 billion times stronger than on Earth. Time at the surface runs noticeably slower than time far away. If you could stand on a neutron star's surface for 1 hour, several hours might pass for someone far away. But neutron stars don't have event horizons. You could still, in principle, escape. Time dilation is strong, but not infinite. Only at the event horizon does time dilation become infinite from an outside perspective. This infinite dilation creates the boundary between inside and outside. It separates regions of space-time that can communicate with the outside universe from regions that cannot. The event horizon is, in a sense, a boundary in time as much as a boundary in space. The mathematics of time dilation near a black hole comes from the Schwarzschild metric, the solution to Einstein's equations for a spherical, non-rotating mass. The metric describes how distances and times are measured in curved space-time. One key term in the metric involves the factor 1 minus the Schwarzschild radius divided by the radial distance. As the radial distance approaches the Schwarzschild radius, this factor approaches 0 and time dilation approaches infinity. This factor also affects the measurement of distances. As you approach the event horizon, radial distances stretch out. A small change in position near the horizon corresponds to a large change in the coordinate distance. This is part of what makes the geometry so strange. Space itself is stretched. Moving outward becomes harder and harder, requiring more and more distance to be covered. At the horizon, it would take infinite distance to move outward, which is another way of understanding why escape becomes impossible. If you were hovering just above the event horizon, you'd need to accelerate constantly to stay in place. The closer you are to the horizon, the harder you'd have to thrust your rockets. At the horizon itself, you'd need infinite acceleration to hover. This is impossible, so nothing can hover exactly at the event horizon. You either orbit around it at a safe distance, or you fall in. There is a special radius called the photon sphere, located at 1.5 times the Schwarzschild radius. At this distance, light can orbit the black hole in circular paths. Photons traveling tangentially at the photon sphere will loop around the black hole endlessly, neither falling in nor escaping. This is an unstable orbit. The slightest perturbation inward will cause the photon to spiral into the black hole. The slightest perturbation outward will cause it to escape. For massive objects, things with mass, there's a similar radius called the innermost stable circular orbit, or ISCO. This is the closest distance at which a stable orbit is possible. For a non-rotating black hole, the ISCO is at 3 times the Schwarzschild radius. Inside this radius, stable orbits don't exist. Any object orbiting closer will gradually spiral inward, eventually crossing the event horizon. The ISCO is important for understanding accretion disks, the glowing disks of gas that surround black holes. Material in the accretion disk orbits the black hole, gradually spiraling inward due to friction and the loss of angular momentum. Once the material reaches the ISCO, it plunges inward rapidly, crossing the event horizon in a final quick descent. This is the point of no returns for orbiting matter. Between the ISCO and the event horizon, orbits are possible but unstable. A spacecraft could orbit there temporarily, but it would need constant adjustments to maintain its orbit. Any small perturbation would cause it to spiral inward or outward. Below the ISCO, all orbits become unbound. Everything falls straight in. The photon sphere and the ISCO are features of the space-time geometry around a black hole. They're consequences of the same curvature that creates the event horizon. These radii mark boundaries where the behavior of light and matter changes. They're part of the layered structure of a black hole's environment. At the center, the singularity. Surrounding it, the event horizon. Beyond that, the photon sphere and the ISCO. And further out, the realm where normal orbital mechanics apply. The concept of gravitational redshift helps explain why light from near the event horizon appears dimmer and redder to distant observers. Light climbing out of a gravitational well loses energy. It doesn't slow down. Light always travels at the speed of light, but its wavelength stretches. Shorter wavelengths shift toward longer wavelengths. Blue light becomes red. Red light becomes infrared. And as light tries to escape from deeper and deeper in the gravitational well, it gets stretched more and more. Near the event horizon, this redshift becomes extreme. Light emitted just above the horizon gets stretched by enormous factors. A photon that starts as visible light might arrive at a distant observer as a radio wave. The closer to the horizon the light originates, the more severe the redshift. At exactly the horizon, the redshift becomes infinite. Light emitted there would be stretched to infinite wavelength, which means it carries zero energy by the time it reaches a distant observer. This infinite redshift is another way of understanding why the event horizon is a boundary of observability. Not only does time dilation make events at the horizon appear to slow down infinitely, but any light from the horizon itself is redshifted into nothingness. The horizon emits no observable light. It's a boundary beyond which we cannot see. Gravitational redshift isn't just theoretical. We observe it in light from white dwarfs and neutron stars. These dense objects have strong surface gravity, and light climbing away from them loses energy measurably. The effect is strong enough that spectral lines from atoms on the surface appear shifted toward longer wavelengths compared to the same atoms in a laboratory on Earth. For black holes, the effect is taken to its extreme limit. If you were falling toward a black hole while watching the universe behind you, you'd observe something strange. Light from distant stars and galaxies would appear blue shifted. As you fall deeper into the gravitational well, you're moving toward light coming from behind you, and you're also in a region where space-time is more severely curved. Both effects cause light from the outside universe to appear shifted toward shorter wavelengths. Blue light becomes ultraviolet. Red light becomes visible blue. The stars behind you would glow brighter and bluer. As you approached the event horizon, this effect would intensify. The universe behind you would compress into a shrinking circle of increasingly bright blue light. The blue shift would become extreme. By the time you crossed the horizon, the light from the entire external universe, its entire infinite future, would appear compressed into a brilliant ring around the black hole. At least, that's what some calculations suggest. The exact appearance would depend on subtle details of your trajectory and the black hole's properties. Once you crossed the event horizon, the view would change entirely. The universe behind you wouldn't be visible anymore in the usual sense. The geometry inside the horizon is so different that concepts like behind you become ambiguous. Inside, every direction points toward the singularity in your future. The past The external universe exists in a direction that's no longer spatial. It's in your past, temporally, not spatially outward. Crossing the event horizon is, in many ways, crossing a point of no return in time rather than space. Outside the horizon, you can move freely in space, inward or outward, though moving outward requires effort against gravity. Inside the horizon, your spatial freedom is restricted. You can move sideways, orbit around the singularity, delay your arrival there briefly. But you cannot move outward in the radial direction. That direction has become time-like. Moving outward would be like moving backward in time, which is forbidden. Einstein's equations tell us that space-time inside a black hole is structured so that the radial coordinate, the distance from the center, becomes a time coordinate. And the time coordinate becomes space-like. This is part of what makes the interior so strange and difficult to visualize. The mathematics is clear, but the physical interpretation challenges our intuition. We're used to space being something we can move through freely and time being something that marches forward. Inside a black hole, those roles swap, at least partially. The singularity at the center of a black hole is not a place in space, it's a moment in time. Once you cross the event horizon, the singularity is in your future, unavoidable in the same way tomorrow is unavoidable. You will reach it, just as you will reach the next moment of time. Asking how to avoid the singularity once you're inside the horizon is like asking how to avoid tomorrow. The question doesn't quite make sense within the framework of the geometry. How long would it take to fall from the event horizon to the singularity? That depends on the size of the black hole. For a stellar mass black hole, a few times the mass of the Sun, the journey would take a tiny fraction of a second. You'd cross the horizon and reach the singularity almost immediately. For a supermassive black hole, millions or billions of times the Sun's mass, the journey could take hours. You could cross the horizon, look around, observe the strange geometry, and still have time to think before reaching the singularity. This might seem paradoxical. How can the interior of a black hole be large enough to take hours to cross when the event horizon is only a boundary? The answer lies in the stretching of space inside the horizon. The radial direction inside is stretched enormously. Even though the horizon itself is at a fixed radius from the singularity, as measured from outside, the proper distance, the actual distance measured by someone traveling inward, is much larger. Space inside the black hole is bigger on the inside, in a sense. The singularity itself is predicted to be a point of infinite density, where the curvature of space-time becomes infinite. At the singularity, Einstein's equations break down. The mathematics produces infinities, which usually signals that the theory is incomplete. Most physicists believe that quantum effects, not included in general relativity, would become important at the singularity and prevent true infinities. But we don't yet have a theory of quantum gravity to describe what actually happens there. So when we say the singularity is in your future if you cross the horizon, we're speaking based on classical general relativity. The real nature of the singularity is unknown. It might not be a point. It might be a region where space and time have a structure we can't yet describe. It might be something else entirely. But whatever it is, it's hidden behind the event horizon, forever out of reach of external observation. This brings us to a concept called cosmic censorship. It's a conjecture, not a proven theorem, proposed by physicist Roger Penrose. The idea is that singularities are always hidden behind event horizons, Nature, in a sense, censors the singularities, preventing us from seeing them directly. Every black hole singularity is cloaked by an event horizon. We never see a naked singularity, a singularity without a horizon. If cosmic censorship is true, it means the universe protects us from the breakdown of physical law. Singularities might exist, but they're always hidden. The event horizon acts as a one-way veil. Information can go in, but nothing comes out. The singularity's details remain private. This seems to be the way black holes work in nature. Every black hole we've observed has an event horizon. We've never detected anything that looks like a naked singularity. There are hypothetical scenarios where cosmic censorship might be violated. If you could spin a black hole fast enough or charge it with enough electric charge, the mathematics suggests the event horizon might disappear, leaving the singularity exposed. But calculations also suggest that you can't actually spin a black hole that fast or charge it that much in practice. Physical processes seem to prevent cosmic censorship from being violated. The event horizon protects the outside universe from the singularity, but it also isolates the singularity. Anything that happens at or near the singularity cannot affect the outside universe. The horizon is a one-way information barrier. Signals sent outward from inside never escape. The interior of a black hole is causally disconnected from the exterior. It's a separate region of space-time, sealed off from the rest of the universe. This one-way causality is part of what defines the event horizon. More precisely, the event horizon is the boundary of the causal past of future infinity. That's a mouthful, but it means the following. Imagine looking backward in time from the infinite future of the universe. The event horizon is the boundary separating events that could send signals to future infinity from events that couldn't. Events inside the horizon are not in the causal past of the external universe's future. They're cut off. Because of this one-way causality, the event horizon is sometimes described as a null surface. In the language of relativity, a null surface is one that light rays move along. The event horizon is made up of light rays that are trying to escape but can't. They're stuck, moving along the horizon, neither falling in nor getting out. These light rays generate the surface of the horizon. It's a surface of light, frozen in place by the extreme curvature. If you were to shine a flashlight outward while standing just outside the event horizon, the light would slowly climb away, redshifted and dimmed, but eventually escaping to distant observers. If you shined a flashlight outward while standing exactly at the horizon, the light would stay at the horizon, moving along the surface. If you shined a flashlight outward from inside the horizon, the light would curve back inward, falling toward the singularity despite being aimed outward. This is the progression as you cross the boundary. The event horizon has zero thickness. It's not a shell or a membrane with any physical extent. It's an infinitesimally thin boundary in space-time. You can cross it, moving from the outside to the inside, but the crossing happens at a specific point in your journey. There's no being in the horizon in the sense of being partway through a thick wall. You're either outside, at, or inside, and being exactly at the horizon is a measure zero event, a single moment in your fall. Despite being infinitely thin, the event horizon has an area. For a Schwarzschild black hole, the area is 4p times the Schwarzschild radius squared. This area is well defined and measurable in principle from the outside. It's the area of the spherical surface at the Schwarzschild radius, and interestingly, this area has deep connections to thermodynamics and information, as we'll touch on later. The event horizon also has a temperature. In a theoretical sense, Stephen Hawking showed in the 1970s that quantum effects near the event horizon cause black holes to emit radiation, now called Hawking radiation. This radiation makes the black hole behave as if it has a temperature. For stellar mass black holes, this temperature is incredibly tiny, far colder than the cosmic microwave background radiation that fills space. But for very small black holes, if they exist, the temperature could be higher. Hawking radiation is a quantum phenomenon. It arises from vacuum fluctuations near the event horizon. In quantum field theory, empty space isn't truly empty. Particle-antiparticle pairs constantly pop into existence and annihilate. Near the event horizon, it's possible for one particle of a pair to fall into the black hole while the other escapes. The escaping particle becomes Hawking radiation. The infalling particle has negative energy from the black hole's perspective, causing the black hole to lose mass slowly. This process is extraordinarily slow for any black hole we've observed. A black hole with the mass of the Sun would take something like 10 to the power of 67 years to evaporate via Hawking radiation. That's far, far longer than the current age of the universe. For supermassive black holes, the evaporation time is even longer. In practical terms, black holes in our universe gain mass faster from the cosmic microwave background than they lose from Hawking radiation. They are growing, not shrinking. But in the far, far future, as the universe expands and cools, and stars stop forming, black holes might begin to evaporate. Over timescales that make billions of years look like an eye blink, Hawking radiation could cause black holes to shrink. Eventually, they might disappear entirely, evaporating into a faint glow of particles and radiation. The event horizon would shrink slowly over eons until nothing remained. But this is so far in the future that it's more of a theoretical curiosity than something observable. Hawking radiation creates a paradox called the information paradox. Quantum mechanics says that information cannot be destroyed. If you know the quantum state of a system at one time, you can in principle calculate its state at any other time. The evolution is deterministic and reversible. But if a black hole evaporates completely via Hawking radiation, what happens to the information about everything that fell into the black hole? The radiation seems to be thermal, random, carrying no information about what went in. This puzzle has troubled physicists for decades. Does the information get destroyed, violating quantum mechanics? Does it somehow escape in subtle correlations in the Hawking radiation? Does it remain encoded on the event horizon in some way? We don't know. Resolving the information paradox likely requires a complete theory of quantum gravity, which we don't yet have. It's one of the deepest mysteries connected to event horizons. Some physicists have proposed that information is stored on the event horizon itself in a kind of holographic encoding. The holographic principle suggests that all the information about a volume of space can be encoded on the boundary of that volume, like a hologram. For a black hole, the event horizon would be the boundary, and all information about the interior would be encoded on the horizon's surface. This is speculative, but it's one way to potentially resolve the paradox. The area of the event horizon is related to the black hole's entropy. Entropy is a measure of disorder or the number of possible states of a system. In black hole thermodynamics, the entropy of a black hole is proportional to the area of its event horizon, not its volume. This is strange. For most objects, entropy scales with volume, but for black holes, it scales with surface area. This is one hint that the holographic principle might be true. Jacob Bekenstein first proposed that black holes have entropy in the early 1970s. He argued that when matter falls into a black hole, the information about that matter becomes inaccessible, which increases the entropy of the universe. To prevent a violation of the second law of thermodynamics, which says total entropy always increases, the black hole itself must have entropy. Hawking's work on black hole radiation provided a way to assign a specific temperature to the black hole, completing the thermodynamic picture. The formula for black hole entropy is simple and elegant. The entropy is proportional to the area of the event horizon divided by 4 times the Planck length squared. The Planck length is a fundamental scale in quantum gravity, about 10 to the negative 35 meters. This formula links gravity, quantum mechanics, and thermodynamics in a profound way. It suggests that the event horizon is not just a geometric boundary, but also a thermodynamic system. The second law of thermodynamics, applied to black holes, says that the total entropy, the entropy of the black hole plus the entropy of everything outside it, never decreases. This implies that the area of the event horizon never decreases, at least in classical physics. If 2 black holes merge, the area of the final black hole's horizon is at least as large as the sum of the 2 original horizons. Area cannot be destroyed. This area theorem was proven by Stephen Hawking in the early 1970s, before his work on black hole radiation. It's a consequence of the general relativistic structure of event horizons. In classical general relativity, event horizons can only grow. Matter falling in increases the mass and thus the area. Mergers increase the area. The horizon is a one-way surface. It can expand, but not contract. Hawking radiation complicates this picture because it allows black holes to lose mass and shrink. So the area theorem is strictly true only in classical physics, without quantum effects. Once you include Hawking radiation, black holes can shrink and their horizons can decrease in area. But this happens so slowly that for any realistic scenario in the present universe, the area theorem still holds in practice. When 2 black holes merge, their event horizons don't simply touch and combine. The process is more complex. As the black holes spiral toward each other, their individual horizons remain distinct until they get very close. Then, at a certain point, a new common horizon forms around both black holes. This common horizon has an area larger than the sum of the 2 original horizons. Inside the common horizon, the 2 original horizons continue to exist for a time, but they're no longer event horizons in the global sense. They're trapped surfaces, regions from which light cannot escape. The merger of 2 black holes is one of the most energetic events in the universe. The collision releases energy in the form of gravitational waves, ripples in space-time itself. These waves carry information about the masses, spins, and orbits of the black holes. By detecting these waves, we can learn about the black holes and test general relativity in the strong field regime. The LIGO and Virgo observatories have detected dozens of black hole mergers by observing gravitational waves. Gravitational waves from a black hole merger have a characteristic signature called a chirp. As the black holes spiral closer, They orbit faster and faster, emitting gravitational waves at higher and higher frequencies. The frequency and amplitude increase, creating a rising tone, like a bird's chirp. Then, when the black holes merge, the waveform peaks and rings down as the final black hole settles into a stable state. The entire signal lasts only a fraction of a second, but it contains a wealth of information. The first gravitational wave detection, announced in 2016, came from the merger of two black holes about 1.3 billion light-years away. Each black hole had a mass around 30 times the Sun's mass. They spiraled together and merged, forming a single black hole of about 60 solar masses. The missing mass, about 3 times the Sun's mass, was radiated away as gravitational wave energy. In a fraction of a second, this merger released more energy than all the stars in the observable universe combined. That's not an exaggeration. For that brief moment, the gravitational wave luminosity of the merger outshone the entire electromagnetic luminosity of all stars everywhere. But this energy was radiated as space-time ripples, not light. We don't see it with telescopes. We detect it with interferometers that measure tiny distortions in space-time as gravitational waves pass through Earth. The distortions are incredibly small, smaller than the width of a proton, but they are measurable with precise instruments. When black holes merge, their event horizons merge too. The final event horizon forms around both black holes, enclosing them in a single surface. The shape of this final horizon is initially distorted, rippling and wobbling as it settles down. These ripples are called quasi-normal modes. They damp out quickly, and the horizon becomes spherical, or oblate if the final black hole is spinning. The ring-down phase of the gravitational wavy signal corresponds to these quasi-normal modes of the event horizon. Settling into its final shape, the no-hair theorem says that black holes are simple objects. Once a black hole has formed and settled down, it's completely described by just 3 properties: mass, spin, and electric charge. Nothing else. No matter what kind of matter fell in, no matter how complex the collapse was, the final black hole is characterized only by these 3 numbers. All other information is lost behind the event horizon. The black hole has no hair, meaning no distinguishing features beyond mass, spin, and charge. Electric charge is almost always negligible for real black holes. Astrophysical black holes form from matter that's electrically neutral overall, and even if some charge were present, it would quickly be neutralized by attracting opposite charges. So in practice, black holes are described by just 2 numbers: mass and spin. Mass determines the size of the event horizon. Spin determines its shape. A spinning black hole is called a Kerr black hole, named after Roy Kerr, who found the solution to Einstein's equations for a rotating black hole in 1963. The Kerr solution is more complex than the Schwarzschild solution. The event horizon is no longer a perfect sphere. It's oblate, flattened at the poles and bulging at the equator, like Earth's shape, but more extreme. The faster the black hole spins, the more oblate it becomes. Spin also creates a region outside the event horizon called the ergosphere. In the ergosphere, space-time is dragged around the black hole so strongly that nothing can remain stationary relative to distant stars. Everything in the ergosphere is forced to rotate in the same direction as the black hole, an effect called frame dragging. You could still escape from the ergosphere, but you couldn't hover without moving. You'd be swept along by the rotating space-time. The outer boundary of the ergosphere is called the ergosurface, or sometimes the static limit. Outside this surface, you can remain stationary relative to distant stars. Inside it, you can't. The ergosurface touches the event horizon at the poles and bulges out farther at the equator. The region between the ergosurface and the event horizon is the ergosphere. It's a strange zone where space-time itself is rotating. Inside the ergosphere, particle paths are dragged forward in the direction of rotation. A process called the Penrose process allows energy to be extracted from a rotating black hole by sending matter into the ergosphere and having it split, with one piece falling into the black hole and the other escaping with more energy than it started with. The escaping piece carries away energy from the black hole's rotation. This slows the black hole's spin slightly. In principle, the Penrose process could extract a significant fraction of a rotating black hole's mass energy. Real astrophysical black holes are thought to be spinning, most of them rapidly. When matter falls into a black hole, it carries angular momentum with it, spinning the black hole up. Mergers also transfer spin. The fastest a black hole can spin is limited by the physics of the Kerr solution. If a black hole spins faster than a certain maximum rate, the event horizon disappears and the singularity becomes naked, violating cosmic censorship. Nature seems to prevent this, keeping black holes below the maximum spin rate. For a maximally spinning Kerr black hole, the event horizon shrinks to half the Schwarzschild radius at the equator. The singularity is no longer a point. It's a ring in the equatorial plane. The geometry is even stranger than for a non-rotating black hole. There are closed time-like curves, paths through space-time that loop back on themselves in time. These exist inside the inner event horizon of a Kerr black hole, though whether they're physically real or artifacts of the mathematical idealization is unclear. A rotating black hole actually has two event horizons, an outer and an inner. The outer event horizon is the true boundary from which nothing can escape. The inner event horizon lies inside the outer one, closer to the ring singularity. Between the two horizons, the geometry is complex. In principle, you could cross the outer horizon, then the inner horizon, and emerge into a region where the singularity is in your past rather than your future. But this region is likely unstable and unphysical in realistic scenarios. The structure of rotating black holes is rich and complex. The Kerr solution predicts features like the ergosphere, frame dragging, ring singularities, and multiple horizons. These features have been studied mathematically, but we can't observe them directly because they're hidden behind the event horizon. What we can observe are the effects of spin on the space around black holes, such as how accretion disks behave and how jets are launched. Jets are narrow beams of high-energy particles and radiation that shoot out from the vicinity of some black holes, particularly supermassive ones at galaxy centers. These jets can extend for millions of light years, far beyond the galaxy itself. They're powered by the rotational energy of the black hole and the magnetic fields threading through the accretion disk. Frame dragging helps launch and collimate the jets. The jets don't come from inside the event horizon. They originate in the accretion disk and ergosphere region just outside. The event horizon itself doesn't emit jets or radiation. It's a passive boundary. But the region just outside the horizon, where matter spirals in and energy is released, is anything but passive. It's one of the most energetic environments in the universe. Matter in the inner accretion disk is moving at significant fractions of the speed of light, heated to millions of degrees, emitting X-rays and gamma rays. This radiation illuminates the darkness of the event horizon, creating the bright ring we see in images like those from the Event Horizon Telescope. The appearance of an event horizon depends on what's around it. A black hole alone in empty space would be invisible, a hole in the star field. But black holes in nature are rarely alone. They're surrounded by gas, dust, and sometimes companion stars. This material glows as it falls inward, illuminating the darkness and revealing the event horizon's presence through its absence of light. When we look at images of black holes like those from the Event Horizon Telescope, we're not seeing the event horizon directly. We're seeing its shadow. The shadow is larger than the event horizon itself because light paths near the black hole are bent so severely that light from behind and around the black hole gets curved around it. This creates a dark region, the shadow, surrounded by a bright ring of light. The shadow's edge is called the photon ring. The photon ring is formed by light that has traveled very close to the black hole, sometimes orbiting it once or even multiple times before reaching us. Light from the accretion disk can take many different paths to our eyes. Some light comes directly, some bends around the black hole taking a longer route. Some loops around once before heading our way. Each additional orbit creates a fainter ring within the bright ring. In principle, there are infinite photon rings nested within each other, but only the first one or two are bright enough to see. The size of the shadow depends on the black hole's mass and spin. For a non-rotating black hole, the shadow is about 2.6 times larger than the event horizon's radius. For a rapidly spinning black hole, the shadow is slightly smaller and asymmetric. The side of the black hole spinning toward us appears different from the side spinning away due to relativistic beaming and Doppler effects. These subtle differences in the shadow's shape and brightness can tell us how fast the black hole is spinning. Measuring a black hole's spin from observations is challenging but possible. One method uses X-ray spectroscopy to study the iron emission line from the inner accretion disk. As the disk rotates, parts moving toward us are blue shifted, and parts moving away are red shifted. The inner edge of the disk extends closer to the event horizon for a rapidly spinning black hole than for a slowly spinning one. By measuring where the inner disk edge is located, we can estimate the black hole's spin. Another method involves measuring the brightness and spectrum of the thermal emission from the accretion disk. The efficiency of converting matter into radiation depends on how close to the event horizon the matter can orbit before falling in. For a spinning black hole, matter can orbit closer and release more energy before crossing the horizon. By measuring this efficiency, we can constrain the spin. These measurements are difficult because they require disentangling many effects: the black hole's spin, the disk's orientation, the viewing angle, and the properties of the accreting matter. But over the past 2 decades, astronomers have measured spins for dozens of black holes, both stellar mass and supermassive. Most seem to be spinning at significant fractions of their maximum possible spin, suggesting they've been fed by accretion disks or grown through mergers in ways that efficiently transfer angular momentum. The event horizon's presence affects more than just light. It affects the fabric of space-time itself in ways that propagate outward. When a black hole's mass or spin changes, the event horizon adjusts. This adjustment sends ripples through space-time, gravitational waves. During a merger, the violent reshaping of the event horizon is the primary source of the gravitational waves we detect. The horizon's dynamics are written into the waveform. From gravitational wave observations, we can infer properties of the event horizons involved in mergers. The final mass and spin of the remnant black hole are encoded in the ring-down signal. We can test whether the object has the properties expected for an event horizon. So far, all observations are consistent with general relativity's predictions for black holes with event horizons. There's no evidence for exotic alternatives like boson stars or Grava stars, hypothetical objects that might mimic black holes without having event horizons. The consistency of observations with event horizon predictions gives us confidence that these boundaries exist. We can't see them directly. We can't send probes to check and report back. But their effects on light, matter, and space-time are precisely what Einstein's equations predict. The mathematics describes nature with remarkable accuracy. The event horizon, despite being invisible and intangible, leaves its fingerprint on everything around it. One of the strangest aspects of event horizons is that they separate observers into different classes. Observers far away see one reality, matter never quite crossing, frozen at the edge, fading to invisibility. Observers falling in see another, a smooth crossing, continued journey inward, eventual arrival at the singularity. Neither perspective is more correct. Both are valid within their reference frames. The event horizon is the boundary that makes these perspectives irreconcilable. This observer dependence is fundamental to relativity. There is no absolute simultaneity. Different observers can disagree about the timing and even the order of events. Near an event horizon, these disagreements become extreme. An event that has already happened for one observer has not yet happened and will never be seen to happen by another. The horizon sits at the boundary between these conflicting accounts. Philosophers and physicists have debated what this means for our understanding of reality. Does the falling observer's reality continue after crossing the horizon, even though the outside observer never sees it happen? Most physicists say yes. The space-time inside the horizon is as real as the space-time outside. The falling observer's experience is real. Their journey continues beyond the point where communication with the outside becomes impossible. But this creates puzzles. If information falling into a black hole is never seen to cross from the outside perspective, in what sense is it inside? The information appears frozen at the horizon, redshifted to invisibility, but still technically there in the outside observer's frame. Yet, from the infalling perspective, it has crossed and is now inside. Which is true? Perhaps both, in different senses. The horizon mediates between these truths, allowing both to coexist without contradiction. There's a concept called the stretched horizon, introduced to help think about these issues. The stretched horizon is an imaginary surface just outside the event horizon, a tiny distance away. An outside observer can think of all the information that falls into the black hole as accumulating on this stretched horizon, encoded in subtle correlations and quantum states. Nothing actually stops at the stretched horizon, but from the outside perspective, the observable effects are the same as if it did. The stretched horizon is a tool for thinking about black hole thermodynamics and the information paradox. If information is preserved on the horizon, perhaps the black hole doesn't truly destroy information. Perhaps the information is scrambled and encoded on the horizon's surface, and then slowly released through Hawking radiation over enormous timescales. This is one approach to resolving the paradox, though it's not proven. Another idea is that the event horizon is a firewall, a region of intense energy that would destroy anything trying to cross it. This firewall hypothesis was proposed to resolve certain tensions in black hole physics, but it creates its own problems. It conflicts with the equivalence principle, which says that freely falling observers shouldn't experience anything special at the event horizon. The firewall debate is ongoing, and consensus has not been reached. The horizon might also be fuzzy rather than sharp, according to some quantum gravity theories. Instead of a precise boundary, there might be a quantum scale region where the classical concept of an event horizon breaks down and is replaced by something more complex. These ideas are speculative, requiring a theory of quantum gravity that we don't yet have, but they remind us that the event horizon, despite being well-defined in classical general relativity, might be more subtle in a complete quantum theory. What we can say with confidence is that event horizons, as predicted by general relativity, match observations. The shadows we image, the gravitational waves we detect, the X-rays we observe from accreting matter, all are consistent with objects having event horizons. If there are modifications or corrections due to quantum effects, they're small enough that we haven't detected them yet. For astrophysical black holes, classical general relativity works remarkably well. The event horizon represents a limit to knowledge. Beyond that boundary, we cannot see. We cannot send probes to report back. We cannot retrieve information. It's a one-way door. This might seem frustrating, but it's also profound. The universe has boundaries to what can be known, at least from the outside. There are regions forever cut off from observation. The event horizon enforces this cut, cleanly and absolutely. Yet even though we can't see inside, we can still learn. The properties of the black hole, its mass and spin, are measurable from the outside. The event horizon's size and shape encode these properties. The way the horizon affects nearby matter and light tells us about the space-time geometry. We're reading the black hole through the language of curved space-time, using light and gravitational waves as our text. In the future, we may observe event horizons in even greater detail. Next-generation gravitational wave detectors will hear thousands of black hole mergers, mapping the population and testing general relativity with exquisite precision. Improved radio telescope arrays might image more black holes, including smaller ones, and study the dynamics near their horizons in real time. Space-based telescopes could observe X-ray and gamma-ray emission from the inner accretion disk with unprecedented clarity. Each observation refines our understanding. Each measurement tests the theory. So far, Einstein's vision holds. The event horizon exists, not as speculation, but as a feature of nature. It's the edge where time, from one perspective, stops, where causality becomes one way, where the universe hides its singularities behind a veil. It's a boundary drawn not in space, but in the geometry of space-time itself. Some event horizons are small, wrapping around stellar mass black holes just kilometers across. Others are vast, surrounding supermassive black holes larger than our solar system. But all share the same fundamental nature. They mark the point of no return, the boundary of observability, the edge where our equations predict something so strange that it challenges comprehension, yet so precise that it matches every measurement we've made. And perhaps that's the deepest wonder of all. The event horizon is real, not just a mathematical curiosity, but an actual feature of the universe we live in. There are places, scattered throughout the cosmos, where space-time folds so completely that time and space exchange their roles, where falling inward becomes as inevitable as moving forward in time, where the future is the singularity and the past is everything outside. These boundaries exist right now at this moment. Some are consuming gas and dust, growing slowly. Others are quiet, alone in the dark between stars. A few are colliding, their horizons merging in bursts of gravitational waves. And all of them, from the smallest to the largest, share this property. They are patient, infinitely patient. From the outside view, nothing ever quite crosses. Time stretches, light fades, and the horizon waits eternal. The event horizon teaches us humility. It shows us the limits of observation. It reminds us that the universe contains mysteries we can circle around, study indirectly, and understand mathematically, but never quite touch. We can measure the horizon's size. We can infer its presence. We can watch matter spiral toward it. But we cannot see what happens at the moment of crossing, because that moment takes infinite time from our perspective. Yet it also teaches us wonder. The fact that Einstein's equations, written down in the early 20th century, predict these objects with such precision is astonishing. The fact that we've now observed them, heard them in gravitational waves, imaged their shadows is extraordinary. We live in an age when the boundaries of black holes are not just theoretical, but observable. When the edge of the knowable has been mapped, at least from the outside. Tonight, as you rest, event horizons exist throughout the universe. Some are at the centers of galaxies, anchoring the slow spiral of billions of stars. Others drift alone through interstellar space, invisible except for the starlight they bend. And at each one, the same physics applies, the same geometry, the same patient boundary where time from the outside stretches toward forever. You are made of atoms, forged in stars. Some of those stars, at the end of their lives, collapsed to form black holes. The matter that didn't quite make it across, that remained outside the horizon, was scattered back into space in supernova. That matter eventually found its way into new stars, new planets, into you. You are connected through the long history of cosmic recycling to the same processes that create event horizons. The universe has boundaries, and one of them is the event horizon. It's invisible, intangible, yet as real as the ground beneath your feet. It's a place where the familiar rules stretch and break, where time bends, where the journey becomes one way. And it exists not in some distant hypothetical realm, but here, in this cosmos, surrounding regions of profound darkness and mystery. As your thoughts begin to drift, as the day fades and rest approaches, consider this. The universe is vast, and most of it is hidden. Event horizons hide singularities. Dark matter hides from light. The future hides from the past. And in all of this hiddenness, there is beauty. Not everything needs to be known. Some boundaries are there to remind us of the limits of knowing and the value of wondering. The event horizon is patient, infinitely so. It waits at the edge of every black hole, the boundary where time slows and space curves beyond return. It's been there since the black hole formed, and it will be there for eons to come. A silent edge, a one-way door, A reminder that the universe contains places we can describe but never visit, places we can infer but never see. And tonight, that's enough. To know that such places exist, to understand even a little what they are, to rest in the knowledge that the cosmos is stranger and more wonderful than we often imagine. The event horizon waits, eternal and patient. And you can rest now, knowing that the mysteries will still be there tomorrow, still waiting, still silent, still holding their secrets beyond the edge of time. If you happen to still be awake, you can watch the next video now, where another gentle journey awaits. If your eyes are heavy, let them close. Let your breathing slow. Let the thoughts of curved space-time and infinite boundaries fade into the soft darkness of rest. The event horizon will be there, at the edge of the knowable, whether you think of it or not, a boundary in space-time, a place where time stops from one view and continues from another, a reminder that the universe is far stranger than we can see, yet precisely as strange as the mathematics predicts. Sleep well, dream softly, and good night.